Imagine a world where language barriers simply melt away, allowing seamless communication across cultures. Sounds like science fiction, right? For decades, achieving truly fluent, context-aware machine translation seemed like an insurmountable challenge for computers. It's far more complex than just swapping words. It involves understanding nuance, idioms, and cultural context, something even humans struggle with at times. We've come an incredible distance from rudimentary dictionary lookups and simple phrase matching to sophisticated AI systems that can translate with remarkable accuracy, even capturing stylistic elements. This journey hasn't been linear, but rather an evolution driven by continuous breakthroughs in natural language processing, or NLP. In this deep dive, we'll unpack precisely how NLP has transformed language translation from a brittle, rule-bound task into a fluid, adaptive process. We'll start by exploring the foundational approaches, then journey through the revolutionary neural machine translation architectures, including the game-changing transformer models. Finally, we'll examine the current challenges, ethical considerations, and exciting future trends shaping this dynamic field. Get ready to understand the why and how behind modern language translation, and perhaps even glimpse its future potential. Before the era of deep learning, machine translation relied on more straightforward, albeit limited, methodologies. The earliest significant efforts were in rule-based machine translation, or RBMT. Think of it as a meticulously crafted linguistic engine. Experts would manually encode vast sets of grammatical rules, dictionaries, and syntactic patterns for each language pair. For example, a rule might dictate how to conjugate verbs or order adjectives. While precise in theory, RBMT systems were extremely brittle. They struggled with ambiguity, exceptions, and the sheer complexity of natural language, requiring immense manual effort to scale up. Then came statistical machine translation, or SMT, a paradigm shift. Instead of rules, SMT learned to translate by analyzing massive parallel corpora, texts that had already been translated by humans. It would identify patterns, calculate probabilities of word and phrase alignments, and then piece together translations based on statistical likelihood. SMT was a significant improvement, offering better fluency and robustness than RBMT. However, its limitations were still evident. It often produced grammatically awkward sentences, struggled with long-distance dependencies, and lacked true semantic understanding. It was essentially a sophisticated phrase book, not a genuine comprehension engine. This set the stage for the next major leap. The real revolution in machine translation began with neural machine translation, or NMT, which leverages deep learning to overcome the limitations of SMT. At its core, NMT often employs an encoder-decoder architecture. Imagine two neural networks working in tandem. The encoder reads the source sentence, processing each word sequentially and compressing its meaning into a fixed-length numerical representation called a context vector or thought vector. This vector encapsulates the semantic essence of the entire input sentence. The decoder then takes this context vector and generates the target language sentence word by word. The challenge, however, is that a single fixed-length context vector can struggle to hold all the necessary information for very long sentences. This is where attention mechanisms come into play. Attention allows the decoder, when generating each word in the target language sentence, to dynamically focus on relevant parts of the source sentence's encoded representation, rather than relying solely on the single static context vector. This selective focus is critical for handling long-range dependencies and producing more coherent, accurate translations, especially for longer, more complex sentences. It was a groundbreaking innovation that dramatically improved NMT performance. While the encoder-decoder with attention was a massive leap, a bottleneck remained: its sequential processing. Recurrent neural networks, at the heart of many encoder-decoder models, process words one after another, which can be slow and makes it hard to capture very long-range dependencies efficiently. This led to the development of the transformer model, introduced in 2017, which completely eschewed recurrence and convolutions, relying entirely on attention mechanisms. The transformer's architecture is built upon stacked layers of self-attention and feed-forward networks, enabling parallel processing of input sequences. At the heart of the transformer is the self-attention mechanism. Instead of attending to a separate source sequence, self-attention allows each word in the input sequence to weigh the importance of every other word in the same sequence when computing its own representation. This parallel capability is a game changer for speed and capturing global dependencies. To preserve word order, which self-attention inherently ignores, positional encoding is added to the input embeddings. Furthermore, the transformer employs multi-head attention, where multiple self-attention mechanisms run in parallel, each focusing on different aspects of word relationships. Their outputs are then combined, allowing the model to capture a richer, more diverse set of dependencies simultaneously. This parallel processing and sophisticated attention is why transformers now dominate NMT and many other NLP tasks. So, where do we stand with NMT today, and what's next? Despite impressive advancements, current challenges in NMT persist. Translating low-resource languages where vast parallel corpora are scarce remain difficult. Domain-specific translation, like medical or legal texts, often requires specialized fine-tuning. Models can also produce subtle errors or hallucinations that alter meaning, especially with highly nuanced or culturally specific phrases. We also face critical ethical considerations and bias. Since NMT models learn from human-translated data, they can unintentionally perpetuate and amplify societal biases present in that data. Addressing these biases is paramount for fair and equitable AI systems. Looking ahead, future directions are incredibly exciting. Multimodal translation aims to translate not just text, but also spoken language and visual cues, creating truly immersive communication. Research into low-resource language translation continues, leveraging techniques like zero-shot learning. Real-time, highly accurate translation for live conversations is becoming a reality. The journey of language translation is far from over, but NLP has truly brought us to the cusp of a globally connected, multilingual future. Keep exploring, keep questioning, and contribute to building these incredible systems.